How do we estimate theta for the Poisson distribution using the maximum likelihood estimator? We've already discussed that the solution to the maximum likelihood estimator is the differential log of the likelihood estimator equal to 0. And this is the likelihood function, which is equal to the product. This sign means the product of the function. So to get the solution to the maximum likelihood estimator, we use this. We take the log of the function, then differentiate with respect to theta. So this is the likelihood function. All we do is just to put it down this way. This sign, like I said, it means products. So we take the product of this function. This function is this, which is the Poisson distribution. So if you spread this out, we get something like this. Theta xi exponential theta all over x I multiplied by theta x2 exponential negative theta x2 multiplied by, and it continues like this to give us theta x I exponential minus theta x I this. So this is what we get. It means that the likelihood function, we group this together. When we group this together, we get something like this. Theta, of course, if you sum this up, you get summation of xi exponential. If you sum a constant, you get n of that constant all over the product of this will still come down. So we'll continue from here. What we need to do is to take the log, like we said first, we take the log first of this function, we take the log of this. So the log of this, the log of the likelihood function, if you take the log of this, you get summation of xi log theta plus, if you take the log of this, the log of an exponential function, you get that function. This is minus summation of if you take the product of this, it will bring us the summation I reading from 1 to n of x. So this is what you get. If you want to rearrange this, it means the likelihood, the log of the likelihood function will give us summation of xi, I ranging from 1 to n, log theta minus n theta minus summation of I ranging from 1 to n log x. So all we need to do is to take the differential of the likelihood function. So if we take the differential, we get something like this. The differential of the likelihood function. If we differentiate this, you get summation of xi all over theta. If we differentiate this, we are differentiating with respect to theta. If we differentiate this, since we are differentiating with respect to theta, we get minus n. This will turn to 1. And if we differentiate this function, since there is no value for theta here, it becomes 0. So it implies that we get something like this. Summation of xi minus n all over theta. This is what we get. Like we said, the solution is when we equate everything to 0. So we equate this to 0. If we equate this to 0, we get this. So all we need to do is to take the LCM, which gives theta all over this multiplied by this, we have summation of xi minus n theta is equal to 0. So it means we have summation of xi minus n theta is equal to 0. That means summation of xi is equal to n theta. So we come here to round it up. Since we have this, we can rewrite it as n theta is equal to summation of xi, I ranging from 1 to n. So we divide both sides. We divide both sides by n. We have n theta all over n is equal to summation of xi, I ranging from 1 to n all over n. So this will cancel this. We are left with theta to the summation of xi, I ranging from 1 to n all over n, which of course is mean. So we have this. It means that the maximum likelihood of theta estimates will be this. Of course, theta is an estimator. That is why we put this cap on top of it.